In this lecture, we're going to talk about the maximum and minimum values of shear stress. So similar to our discussions of the octahedral shear stress, tau octahedral, we can find values and orientations of maximum and minimum shear stress, or extremal values of shear stress. Now for this discussion, we're going to do what we did when we talked about the octahedral shear stress. We're going to again start with our coordinate system aligned with the principal stress directions. So we would assume that we've already gone through and done the eigenvalue problem to find the directions of our maximum principal stresses. Instead of using an arbitrary x, y, and z coordinate system off at any particular orientation, we're going to use a 1, 2, and 3 or x, y, and z coordinate system aligned with these principal stress directions. So we can imagine that maybe there's a sigma p1 and a sigma p2 and a sigma p3 that we have identified, and we know that they're going to be mutually perpendicular directions because of the eigenvalue problem. Now when we did find tau octahedral, we used a unit normal of 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3 with those components. But now we want to use a more general unit normal to find the orientations to our extreme values of shear stress. So let's go ahead and write that down. Again, it's also important to keep in mind that this is a unit normal. And so if we have components n1, n2, and n3, we do have the restriction that n1 squared plus n2 squared plus n3 squared is equal to 1. All right, let's make a little bit of room. Let's talk about our traction vector again. Alright, so let's recall our traction vector relationship that we have. A general traction vector t can be found by our stress tensor operating on our unit normal n. So t is equal to sigma n. If we were to use our index notation, we would use t sub I is equal to sigma ij nj. Now for our particular coordinate system that we're using, we are in the principal stress directions. So our stress tensor is diagonalized already. So we have sigma p1, sigma p2, and sigma p3 along the diagonals. And these are in no particular order. It's just whatever we want to call or think of as our 1, 2, and 3 direction, or our x, y, and z direction. All the shear terms are 0. I think we've gone through and we've shown that we don't get any shearing stress on the maximum principal stress planes. But we'll see that for sure if we haven't done that already. So for our particular stress tensor sigma then, the components of the traction vector, t1, t2, and t3, which I'll write out in a column format, it's going to be this particular stress tensor, times that unknown and arbitrary yet constrained unit normal vector n. So if we do this multiplication, the vector that we get for the traction vector, because we have so many zeros in here, the vector that we get for that looks like this: sigma p1 times n1, sigma p2 times n2, and sigma p3 times n3. If we wanted to write the vector out in our orthonormal basis, we would say that it looks like this. Sigma p1 n1, that's in the e hat 1 direction. Sigma p2 n2 in the e hat 2 direction, and sigma p3 n3 in the e hat 3 direction. Now, let's look at this from the perspective of the Cauchy tetrahedron. We have some plane there that has a unit normal n, whatever we want it to be. And this traction vector t doesn't necessarily point in the direction of n. It can be skewed off in any particular direction. Depends on the values of these weights, sigma p1, n1, and so forth. And so I'll draw that in on this picture as if it maybe is coming over in this direction. Alright, now we want to do a couple things with this, and we've done this already. We found the shear stress and the normal stress on our particular plane. So we're going to go ahead and do that again. If I wanted the normal stress on the plane, I would take this traction vector t and I would dot it with our unit vector n, and then I would multiply it by the direction vector n to get that vector that points off in that direction. Okay, so schematically, let me see if I can change colors here. Schematically, if I were to draw this component would be the portion of t that's parallel to the unit vector n. And at right angles to that, I would have this component, and this is the portion of t that is perpendicular to the unit normal n that still adds up to be a resultant of my traction vector t. If we want to do the math to find the magnitude of t parallel to n, the way we would write that is the magnitude of t parallel to n squared is equal to t dot n in the n direction. That's the vector, and we can square that magnitude. Now t dot n is itself a scalar, okay? So we can make this t dot n squared, and then we have the magnitude of n squared, which is n dot n, but n dot n is 1. So what we end up with is the magnitude of t parallel to n squared is equal to t dot n squared. All right, actually, I don't think I need the square on this one. I think that's, either way it's irrelevant since the magnitude of n, since n dot n is equal to 1. All right, so if we evaluate t dot n, here's our vector t, and multiply that by n, t dot n is going to be equal to sigma p1 n1 squared plus sigma p2 n2 squared plus sigma p3 n3 squared. T dot n times the unit vector n is going to be all of that times my unit normal vector right there. And so t dot n squared is going to be this line right here squared. It's going to be sigma p1 n1 squared plus sigma p2 n2 squared plus sigma p3 n3 squared. That whole quantity squared. Alright, so if we look at the picture that has the arrows on it, those vector arrows, we can use the Pythagorean theorem again. We can look at this picture and see that the magnitude of the vector t squared is going to be equal to the magnitude of t parallel to n squared plus the magnitude of the vector t perpendicular to n squared. Now what I really want is I want the magnitude of this term right here, magnitude of that vector. We can do that by rearranging that equation. The magnitude of t perpendicular to n is going to be the square root of the magnitude of t squared minus the magnitude of t parallel to n squared. Alright, so we found the magnitude of the second term, t parallel to n squared. Now we need to find out the magnitude of t and square it. So the magnitude of t squared is equal to t dot t. And we had defined what t was equal to. So this is sigma p1 squared n1 squared plus sigma p2 squared n2 squared plus sigma p3 squared n3 squared. So that means that what we want, t perpendicular to n, I'm going to square it. I'm going to square both sides to make this a little bit cleaner. It's going to be what I just wrote down, sigma p1 squared n1 squared plus sigma p2 squared n2 squared plus sigma p3 squared n3 squared minus the quantity sigma p1 n1 squared plus sigma p2 n2 squared plus sigma p3 n3 squared, quantity squared. And what t perpendicular to n is, what it physically represents, is our shearing stress squared, which I'm going to call just tau squared. Alright, so starting with our principal stress directions, using an arbitrary unit normal vector, this expression tells me what the shearing stress is that's acting on that arbitrary plane. It has a unit normal n1, n2, n3. Now what we want to do is we want to be able to select particular values of n1, n2, and n3 that correspond to extreme values, maxima or minima, of our shearing stress, tau or tau squared. And again, we are still subject to the constraint n1 squared plus n2 squared plus n3 squared is equal to 1. Let me write a little bit of that down. And so to do this, we're going to use the Lagrange multiplier technique as described in our book. Now I will say we're going to use this technique. We're not going to be able to go through where this technique comes from and so forth. But if you take a class in advanced calculus, it's probably in there. Right, let's make a little bit of room, and it's going to take a little bit of algebra to get through this, but the results that we're going to get are kind of important. Alright, so we're going to come up with a function f that's going to be tau squared plus lambda squared, which is our Lagrange multiplier, subject to the constraint, which is incorporated into this by n1 squared plus n2 squared plus n3 squared minus 1. And what we want to do is we want to find stationary values of f. Now these occur when we have the partial derivative of this function f with respect to, say, for example, n1 equal to 0, partial of f with respect to n2 is equal to 0, and the partial of f with respect to n3 is equal to 0. So what we're going to do is, from our previous page, we had our expression for tau squared. We're going to take the partial derivative of tau squared with respect to n1, n2, and n3. Alright, so let's do it with respect to n1. Let me call up our equation for tau squared so we have that handy. Alright, so we want the partial of f, so let's first work on one of these terms at a time. Partial of tau squared with respect to n1. So I have my tau squared over there. So keep an eye on me, let's make sure I get all these terms right. So I'm going to have a 2 sigma p1 squared n1, and then I don't have anything from these other two terms because they're not a function of n1. Okay, next I'm going to have a minus 2 because that term in the brackets is squared. I'm going to have everything in the brackets, sigma p1 n1 squared plus sigma p2 n2 squared plus sigma p3 n3 squared. Now it's to the first power because I reduced the exponent. And now we need to take the derivative of the term in the square brackets with respect to n1, which is going to give me a 2 sigma p1 n1. Now I need the partial derivative of the term with the lambda in it. So it's lambda squared times n1 squared plus n2 squared plus n3 squared minus 1 with respect to n1. Now, if I multiply the lambda squared through here and take the partial derivative with respect to n1, the only term I get out of it is a lambda squared times 2n1. So with this, partial derivative of f with respect to n1, are those two terms added together, I'm going to have 2 sigma p1 squared n1, and have a minus 2, the term in the brackets. I'm just going to write it like that to save a little space, times 2 sigma p1 n1, and then I'm going to have a plus 2 lambda squared n1, and for the stationary value I'm going to set it equals 0. Now for the stationary value, having it set equal to 0 means I can get rid of these leading 2's from each of those terms. So we're going to have an equation that looks like this. Sigma p1 squared n1 minus, term in the bracket, I'm going to go ahead and write it out this time, term in the bracket times 2 sigma p1 n1, and then I'm going to have a plus a lambda squared n1. Now I can take the partial derivative of f with respect to n2 and n3 and get some very similar equations. Let me write all of these down. And so with the full set of partial derivatives we have here. So one way to visually think of this is if you take your hand and form a triad with your fingers. 2 fingers and the thumb works pretty well. You take and form a triad with that. What we're trying to do is we're trying to orient that triad with respect to our principal stress directions such that we end up with extreme values of our shearing stress, either maxima or minima. Well, what values can work to make these things equal to 0? Again, just as a reminder, I know I've said it a few times already, but we still have this constraint. n1 squared plus n2 squared plus n3 squared is equal to 1. Well, let's try something. Let's take n1 equal to 0, and n2 is equal to 0, and n3 equal to, we can go either plus or minus 1. Okay, let's see what that does. If n1 is equal to 0, the first equation is 0. If n2 is equal to 0, the second equation is 0, because it's got an n2 right here, in this term, this term. Now if n3 is equal to 1, then we're left with the third equation giving us sigma p3 squared, it's plus or minus, minus, term in the bracket, sigma p3 squared, we're not there yet, sigma p3 times 2 sigma p3 times plus or minus 1 plus lambda squared times plus or minus 1. It'll all be equal to 0. Now we're going to look at the plus 1 solution. If we look at the plus 1 solution, the minus 1 will give us the same kind of equation. The plus 1 solution is going to be sigma p3 squared minus 2 sigma p3 squared plus lambda squared, and that equal to 0. So if we combine these, that's a 3 right here, if we combine these terms, we're going to have lambda squared equal to sigma p3 squared. And if we take the square of both sides, at least we have plus or minus sigma p3. The sign isn't that important right now. We're going to use the solution lambda equal to sigma p3. Now this will give us an extreme value for our shear stress. Let's go back and write down what our shear stress equation is, and we'll plug this value in and see what we get for this extreme value. Okay, so here's our equation for our shear stress squared. And in this one, what did we say? We were taking N1 equal to 0, and N2 is equal to 0, and we're taking N3 equal to plus or minus 1. Let's use the positive root here. So 0, 0, and sigma P3 squared minus 0, 0, and sigma P3 squared. And what do we get? We get tau squared is equal to 0, so the shear stress is equal to 0. So an extreme value, it's the minimum value of shearing stress for a particular stress state is going to be 0. And it is aligned with our principal stress directions. So here now we've shown that in our principal stress directions we don't get any shearing stress. Now we did this for the 0, 0, 1 direction, but if you do the math, it works out to be the same if you do 1, 0, 0 or 0, 1, 0. Those other two directions we don't get any shearing stress either. So that's kind of important. So we have no shear stress in any principal stress direction. Now it shouldn't be a huge surprise because we kind of defined our principal stresses as directions in which there are no shear stress. But either way it works out, this is the case. We don't have any shear stress in these directions. A more interesting case, though, is when we have the maximum shearing stress, and we're going to find out which directions those occur in. Well, I guess before we do that, we can talk about one more degenerate case. There is a particular degenerate case where we can minimize that function, and that is this special case. Put a line here so we know we're talking about a different case. A special case where all three principal stresses are the same. If all three principal stresses are the same, we have a hydrostatic or a spherical stress state. And in that case, it doesn't matter what value of n that we use, we're going to get tau squared equal to 0, or tau is equal to 0 from that case as well. This is pretty easy to see if we look at our shear stress squared equation up here. If sigma P1, sigma P2, and sigma P3 are all equal to each other, then it'll work out that they all cancel out with all these different terms that we have here. Alright, so we don't get any shear stress in that case. So the more interesting case is when we do have a shear stress. And so we're going to take a look at another possibility. And that is if one of these is equal to 0 and the other two are not. Let's make a little room. Alright, so if n1 is equal to 0, the top equation will be equal to 0 right away. And if n2 and n3 are not equal to 0, but n1 is equal to 0, we reduce the second two equations a little bit. So we're going to get an equation that looks like this. I'm going to write with the n out in front. N2 sigma P2 squared minus the quantity. Okay, n1 is 0. N2 squared sigma P2 plus sigma plus N3 squared sigma P3 times 2 sigma P2 into plus lambda squared n2. That equals 0. And then the third equation will reduce down to something that looks like this. N3 sigma p3 squared minus N2 squared sigma p2 plus N3 squared sigma p3 times 2 sigma p3 N3 plus lambda squared N3 equal to 0. Okay, now what we want to do is we're going to solve this system of equations by solving each of these equations for lambda squared and then set them equal to each other. Alright, so the top equation I'm going to divide through by n2. I'm going to keep an eye on my algebra here. I'm going to have a sigma p2 squared minus this term in the brackets times 2 sigma p2. I've divided through by n2. And on the other side, I'm going to have the second equation, the bottom equation, where I've divided through by n3. It's going to look like this. Sigma p3 squared minus the term in the brackets, n2 squared sigma p2 plus n3 squared sigma p3 times 2 sigma p3. Now I'm going to move all the terms on the right-hand side over to the left-hand side. So a little bit of algebra here. I'll pause the video and do the algebra, and you can see the result. Okay, so I want to explain this step before taking the next one. So I've just taken all the terms and written them onto the left-hand side and set that expression equals 0. So I have sigma p2 squared minus sigma p3 squared. I have minus the two terms from the left-hand side. And I have a positive on the two terms from the right-hand side. Okay. Now, this looks a little bit weird in the fact that there's not an n multiplied by these leading terms. And this is a little bit tricky here. The form that we want to get it in is going to be kind of reduced. And the trick that we're going to use is, if you remember, n1 squared plus n2 squared plus n3 squared is equal to 1, but here we have n1 is equal to 0. So here, n2 squared plus n3 squared is equal to 1. So what I'm going to do is I'm going to multiply the leading term by 1. And then I'll have all the rest of the terms. If I haven't written any mistakes in here, I'll have all the rest of those terms, and now I can do some manipulations on that, and this will all end up reducing down to a term that looks like this: n3 squared minus n2 squared times the quantity sigma p2 minus sigma p3. If you're not convinced that that's actually how that factors out, what I would recommend is that you expand the bottom term out, and then you expand the term that I have right above it, and see if you end up with the same thing. If I haven't made any mistakes, then you should. Alright, now there's a couple of ways that this could be 0. Right? One way is if sigma p2 and sigma p3 are both equal to the same thing. Now, if that is the case, that's kind of a special case where we don't have any shearing stress in the plane sigma p2, sigma p3. If you think about Mohr circle, we'll talk about Mohr circle soon, but if you've had this class, if you're taking this class, chances are you've had a class in mechanics of materials. If you think about a class in mechanics of materials where the in-plane normal stresses are equal, you have an equal biaxial stress state, Mohr circle is a point and you don't have any shearing stresses develop. So that is kind of a derivative solution where we don't have any shear stress. The more interesting solution for us is the other one, where n3 squared minus n2 squared is equal to 0. Well, what does that mean? That means n3 squared is equal to n2 squared. And both of these, n2 and n3, would then be equal to plus or minus 1 over the square root of 2. In terms of direction cosine, that means 45 degrees. Right, so our full set for this particular case that we're looking at is a unit normal vector that looks like this. Zero plus or minus 1 over the square root of 2 plus or minus 1 over the square root of 2. Well, let's plug these values in to our shear stress equation and see what value of shearing stress that we get for this particular direction cosine, again oriented from the principal stress directions. So for those particular direction cosine terms, those particular values of n1, n2, and n3, if we plug in, our shear stress squared equation reduces down to this. Remember, n1 is equal to 0. Sigma p1 squared times 0 plus sigma p2 squared times a half plus sigma p3 squared times a half times this quantity 1/2 sigma p2 plus 1/2 sigma p3. Now, let's go ahead and work with this just a little bit. We'll do a little bit more algebra. The first two terms we're going to write down this way. We have a half. I'm going to pull it out in front as a quarter. We're going to have a sigma p2 quantity squared. We're going to have a 2 sigma p2 sigma p3, and then we're going to have a sigma p3 squared if I want, I can pull out a quarter from everything. It's going to leave me with a 2 sigma p2s and 2 sigma p3s. It's going to leave me with a minus sigma p2 squared and a minus sigma p3 squared and a minus 2 sigma p2 sigma p3. Okay, that term and that term can reduce, and that term and that term can reduce. This actually is squared here and is squared here. Okay, that should have been carried through as a squared term right there. Alright, so this term and that term can reduce, that term and that term can reduce down. So we're going to have a sigma p2 squared minus 2 sigma p2 sigma p3 plus a sigma p3 squared term That's going to be equal to 1/4 of sigma P2 minus sigma P3 quantity squared. Now this is the shearing stress squared, so if we take the square root, we have a plus or minus a half quantity sigma P2 minus sigma P3. Okay, now that's an important result for us. The maximum values of shearing stress are going to be 45 degrees in between each pair of normal stresses, each pair of principal stresses. So in this case, we're looking at between the 2 and the 3 directions. 45 degrees in between the 2 and the 3 principal stress directions is going to be extreme value of local maximum shearing stress. The value of local maximum shearing stress is going to be 1/2 of the difference between those principal stresses. Now we can do the same thing. We go through all the algebra again and let N1 and N3 be equal to each other, and N2 is equal to 0, N1 and N2 equal to each other, and N3 is equal to 0, and we'll end up with similar expressions. Get my plus and minus here. Alright, so this would be for the unit normal vector 0, 1 over the square root of 2, 1 over the square root of 2. This would be the case for, let's see, we'd have 0 here, and 1 over the square root of 2 in the other two. And then the last case would be 1 over the square root of 2, 0, 1 over the square root of 2. Alright, so those 3 cases in those 3 directions, again with respect to the principal stress directions, are going to be the local extrema of the values of the shearing stress. Now something that we call the absolute maximum shearing stress is going to be the biggest magnitude of all 3 of those. So just to differentiate these a little bit, let's call this one 2, 3. Let's call this one 1, 2. Let's call this one 3, 1, or you call it 1, 3. The absolute maximum shearing stress is going to be the biggest magnitude. So we have the set of tau 2, 3, tau 1, 2, and tau 3, 1. Now one thing that we can't necessarily do with these equations is we can't necessarily tell you if the shearing stress is pointing towards you or away from you. Okay. But we can figure that out if we kind of look at the problem more physically, or if we look at the problem through the perspective of a Mohr circle. And so the Mohr circle is what we'll kind of go through next. Now the Mohr circle is not generally used for arbitrary three-dimensional stress states, but it can be used for something called generalized plane stress. It can give a lot of graphical insight into stress rotations in the plane of a material. So we'll try to do that in the next lecture.